let's read off the physics of the standard model. No dynamics, still statics, if you wish. Let's figure out the particle masses, which we started last time. So the standard model, here is the summary once again to have all the essential features, right? When I say that the group is SU2 plus SU1, gauge symmetry, that's defining my covariant derivative or vice versa, if you wish. Commutation here, when I say that this it's a direct product, implies commutation or vice versa. So this is the way you build any theory, even beyond the standard model. You define your gauge group, then you define your method. Method, this is fermions, quarks and leptons, the constituents of the universe. Then of course you have to do the symmetry breaking that specifies the Higgs. We said we needed a doublet in order to give quarks and leptons the masses. There could have been other multiplets to give W and Z masses, but not for quarks and leptons. And we found out from d mu phi square, written symbolically, well, let me write it once carefully. And let me write this unitary. Remember, I'm in the unitary gauge, where by rotation I simply wrote 0 V plus H. I put a half here. Sometimes I won't do that, then I'll have to put here 1 over square root of 2. It's just a convention of defining my fields. And this gave us, remember, mw square, w plus, or let me better write what we found out, 1/2 mw square a1 square plus a2 square plus 1/2 mz square z mu remember, there is always 1 plus h over v squared. I may write it, sometimes I may not. It comes from here, right? I can simply write this as v, 0, 1 plus h over v. Therefore, whenever I get, and just to remind ourselves, mw was 1/2 gv, the same v which is here, the vacuum expectation value, and mz, you remember? We found out that mz is bigger. mw is mz cosine theta w. Where I have defined the field w plus minus a1 minus plus ia2 over square root of 2. We will see the signs once again when we write the interactions that we wrote before. At the moment it was not clear whether I should put minus, plus, minus, okay. And z was cosine theta w x3 minus sine theta w b. That was the field. I'm not writing the mu index, which sometimes I will, sometimes I won't. This was the field that got the mass. This is what I found out from here. Right? Just by plugging in. Okay, let's remember, that's what we did on Wednesday. Therefore, there had to be a orthogonal field, which didn't appear in the mass term. Which I suspect to be my photon. I mean, this is, I predicted now, a massless gauge boson. I suspect it will be the photon, because it turned out that the way I wrote the vacuum expectation value, the charge was unbroken. You know, I always claim that there is no dependence on the direction of symmetry break, and people are sometimes confused and they say, well, why don't you put here the valve? You know, with my conventions, this is a positive charge field. Remember, the T3 is plus sigma 3 over 2. Therefore, the upper component has more charge. So this is my convention. Then you can say, well, but you could have done put the valve here, then you will break charge. No, because I would just then redefine the charge with the opposite sign in the hypercharge. Or better to say, here's when we said, when there is a field phi, which transforms as u phi under SU2, there is always an anti-field. After all, when there is an electron, there is a positron. Whenever you have a complex field, you have an anti-field. That's the beauty of quantum field theory, right? For every particle, there is an antiparticle, which is simply a complex conjugate, which was I sigma 2 phi star. Sigma 2 is just the famous charge conjugation, quote unquote, okay? And phi tilde transforms into u phi tilde. Phi tilde would have a neutral component above. So you see, if the wave is in that direction, then I would call phi tilde phi, and vice versa. It's a name that I associated with my conventions. I've chosen a convention here. What was crucial about this convention that Q electromagnetic acting on phi 0 is 0. Phi 0 is or acting on phi. They are in the same direction. This is telling me that both the vacuum expectation value and the Higgs field are neutral. One linear combination will always end up being that because I have two diagonal generators, and therefore one linear combination must be preserved, which depends how you write these coefficients. Okay, this is here the essence of the gauge boson and Higgs structure. It's in these few formulas. Of course, there is a lot of physics. I can read off immediately the interactions of the Higgs with my, so there is a master. This is the solution to the issue of W and Z masses, is here. Okay, with an additional prediction. By the way, tangent theta W was, of course, G prime over G. If you wish, from here we can have the interaction of the Higgs, the leading term. What would I get? By the way, from here, A1 square plus A2 square is W plus W minus. That's the normalization. There is a relative factor of 2, both in the mass term and the kinetic energy. So there is always a relative overall factor is the same. So I will get here, so I will get a factor of 2 here, right? I will get n W square, W plus W minus, and then I will get 1 over V. Or maybe 2 over V. Correct? Yes. Plus, here there is a factor of 2 gone, here it stays, so there is 1/2 mz square z mu. Why do I write z square? Well, z square. Let's sometimes not write it. So 2 over v is overall. Sorry, that my privilege of the book. There is a relative factor of 1/2 only because of my complex definition of. So what is this? I should read off here. V, I know what it is. 2 over V is G over MW. So I will get H, G, MW, W plus W minus. I will have 1/2. Am I right? Yes. I think it stays there. This is mz square I will have G, but I will use this relation, so I can write this as G over cosine theta W, and I let you stare at it, Z, Z, and let me now put the indices if you wish. Sometimes we can do that. This will be the interaction. I had mz squared over mw, but I wrote it mz squared over mz, so I have an extra cosine theta w from here. I've used that. Just to emphasize, what I expected. Remember what I said? The Higgs, we already guessed that. The way it appears together with the vacuum expectation value. It will give you a mass, if you mass it, and then it will couple to you proportional to your mass and to the relevant coupling. And we have seen already, you had the homework already, now we'll check it again, because now we have derived the existence of the Z boson and the photon automatically from the symmetry breaking. I didn't assume a photon and that, okay, we'll do it in this way, which is normally done in the books. And remember that the G over cosine theta W was the coupling of the Z boson, okay, that goes into the current. So the usual formula, factor of 2, is just the normalization of the W field. And let's check what we expect, that this will really be the photon. This guy is massless. And remember, strictly massless. You can't have a small mass. The minimal standard model says photon is massless.
Are they 1/2 and 2 factors, right? I cannot see from that.
I think so. Well, there will be here 1/2 A1 squared plus A2 squared.
Yes.
Look, let's check it in the limit theta W goes to 0. When theta W goes to 0, what happens? It's an interesting limit, it's an important limit, because then I go to the SU2, which is nice, which we understood when we studied to some degree. We'll now do a little more. When theta W goes to 0, MC is equal to MW. What is Z boson in that limit? Well, it's simply A3. And therefore, MW is simply A1 and A2 with the same, there will be a half coefficient, and I should get this universal thing that I claim there is a custodial symmetry. We'll prove it explicitly today. But we already guessed that there was this SO3 symmetry, which was making sure that the 3 gauge fields of SU2 remain connected, strangely enough, after symmetry breaking, because there was a residual global symmetry. But I'll do it again. You may have forgotten that. So I think this is correct. Simply because W plus W minus is a halfway A1 square, A2 square. It's a complex way of writing. If I write in the real components, which I could. But it's much more convenient to use W than this, because these are eigenstates of charge. You and I work with an electron and positron. It's much better. We could work with a, half a square of 2 electron plus positron, electron minus positron. It would not be so useful. At the end, of course, what will happen, only electron will couple one way and only positron. So this notation is only more convenient, but it's not necessary. Okay. We said we'll check the coupling that they come out right. They come from here. So whenever you have a fermionic field, you have Fi F bar minus I in the. So why do we write I and minus I from the covariant derivative? In other words, F bar gamma mu d mu Fi gives me this. Then I have gamma mu, and then I have P3. What do I have? A3. I'm looking at the neutral guy. Plus G plus G prime. Y over 2 I write as Q minus T3. Why do I do it? Because I don't know what Y is. I know what Q is. I've learned it. And this is B. And we can put the index mu. This will be interaction of these guys, you agree? which I can write as F bar gamma mu T3. Let me isolate T3. I will get GA3 minus G prime B mu plus G prime Q B mu F. What is this? This is a Z boson. I'm lucky. See, it's simpler this way. In the case when we didn't know about symmetry breaking, we had to define the photon, look at the orthogonal states. Here it came out. This is my Z boson, if you pay attention here, because this is cosine W. In other words, this is F bar gamma mu square root of G square plus G prime square T3 Z mu plus G prime. Let me write G prime as G tangent theta W. And this, by the way, I could have written immediately. This is G over cosine theta W. Agree? By definition. And what is B? I read off from here. B is Q. B is cosine theta W A mu minus sine theta W Z mu. Allow me the privilege of the blackboard. I should have done this immediately, it was obvious. This was G over cosine theta W. You see, because of charge being unbroken, the massless gauge boson, which I suspected corresponds to charge, what else could it be? Okay, the unbroken symmetry, a massless gauge field, couples proportional to Q. This is my photon. So I get F bar gamma. Let's write like this: G over cosine theta W Z mu F bar gamma mu T3. I have T3 here. Here I have sine squared theta W over cosine theta W, which I took out. So I get minus sine squared theta W Q. This is what we expected. The massive guy has to be. Glesio told me, Glesio said if there is a photon, there'll be a massive guy that will look like this. Well, we got it. There is an advantage to spontaneous symmetry breaking. It is simply more predictable. Okay, it says it has to be there. And the second guy is, I can call a photon. With a universal coupling as long as G is E over sine theta W. This is what I promised you before. Weak interactions are stronger than electromagnetic. A little stronger. Theta W is not. It's not one, right? Sine theta W is like a half. Nothing weak about weak interactions, right? We know, well, we have unified them, how can they be weak? They looked weak because W boson is heavy, so when I looked at lower energies, the guy doesn't want to propagate, doesn't want to mediate anything. Okay.
I have a kind of fundamental question. Maybe we answered it, I'm not sure, but the motivation that we introduced that Weinberg angle as an angle.
Well, there was no. I wouldn't call it a motivation. I have two couplings. So I have to decide with what to work.
Yes, but first...
I could work with G and G prime. I don't have to introduce it, so there is nothing into it. Motivation was just notation, nothing else.
But they somehow fit for the a triangular trigonometric relation, like it's something extra. Is there a reason for that?
Well, look, I've sent you Weinberg's paper in 1967. Notice that there is no sine theta W. There is no theta W. He works with G and G prime. And then the formulas are a little more complicated. Why this is sort of nice? Because you know that these guys should be orthogonal rotations of the original fields. I want to normalize it the same way. And I've defined Z. I've normalized. It's hidden here in the normalization. Therefore, it's convenient to call this cosine theta W and not G over square root of G squared plus G prime squared. I won't see as quickly as I will by its only notation.
Yeah, but I was going to say that maybe there is some kind of symmetry that we can rotate inside the third generator and...
No, G and J prime are completely independent. And theta W is arbitrary. There is something to it when we go, suppose that you and I want to grade unify to say, oh, I don't want this U1, I want everything in one big, beautiful, non-abelian, simple group. Then, of course, it has to come from some algebra will determine this, and theta W will come out to be a number, predicted. I can tell you a bit about it at the end. But at this point, it's just notation. It used to be called Weinberg's angle. It's interesting. This is weak mixing angle, as we call it. But Weinberg did introduce it. He introduced it later in 1972 in one of his papers. Okay. If you look at the glacial papers in 61, he actually has the mixing angle. But I think it's pi over 2 minus theta glacial would be pi minus 2 minus theta Weinberg. It's a weak mixing angle, okay? We should not associate it. Anyway, it would be trivial to give a name of a person in some sense, because it's just, there is no thought to this. Okay. So we are happy. This is my photon, right? And the reason, okay, that I've chosen theta W is the same reason that other people took. It's convenient because we are used to E. So you could work just with E and theta W. It's interesting, and people give you E and theta W, they also give you G. Somehow, because a lot of calculations are done with the W boson, people sort of overdo it. So I will give you these numbers, okay, the value of these couplings. There is alpha electromagnetic, which is E squared over 4 pi, and then we introduce often alpha weak, which is G squared over 4 pi. And the good thing to remember that these couplings, by the way, depend on energies. We used to quote alpha as 1 over 137. That's at very low energies. It's not a useful number because we don't do this physics anymore. We will never do that. What we will do very often is the physics at the scale of weak interactions, MW or MZ. Remember I told you the couplings change logarithmically, so whether I put here MW, MZ is irrelevant, that there is no change basically. Right? And this is roughly, I think, 1 over 128. Actually, I remember this 1 over 120 very often because I remember alpha weak at MW to be roughly 1 over 30. And the ratio between them is sine squared at W, which is basically 1/4, roughly. If you remember these numbers roughly, okay, I'm happy now. What we need to remember, however, that they're both very small and we can do happily and successfully perturbation theory. We are lucky. As the energies increases, okay, alpha electromagnetic gets a little bigger and bigger, but sufficiently slowly that it stays very big. For a long time, it will stay smaller than MW. Eventually, of course, they may, catch up with each other. But we will have to plot that, and we will have to know how they run. We'll do that. We'll do that. Today, this is all you have to remember. The thing to worry about before I turn to fermion masses, which are a beautiful topic because among other fermions there is neutrino, right? This crazy, mystical, aloof, strange particle that doesn't want to talk to us, basically. Right? As we speak, there are billions of them passing through us. It's crazy. You've read this poem by Updike, Cosmic Gold? Updike is a famous American writer. It's not as known in Europe, and maybe even less in other parts of the world. Well, he's considered one of the greatest writers by Americans. Well, he died. It's a beautiful poem about neutrinos. Well, we'll talk about neutrinos, so I'll remind you. Okay, it's kind of reassuring to see it explicitly. I like to do that. I knew this had to happen, but it's good to see it. So I pause for a minute to see if you have a question. Then I want to go back and answer what I started on Wednesday. I didn't want to do it because I wanted us to grasp this 5 tilde field and use the physics and mathematics of it. I want to go back and answer this question where I stopped. Why are these masses the same in the limit theta w going to 0? It's very strange that they are the same, right? We said it's SO3 symmetry. Let's identify it explicitly. So I'll erase this. And try to keep this. And the question is, why mz equal mw when theta w 0? Answer is there is a custodial SU2 equal SO3 if you wish, better symmetry. Custodial means protective, and this is a global symmetry that remains after symmetry breaking. And we said, well, the potential had SO4, and then it broke down to SO3, but it was not easy to see how the gauge wasn't transformed under that SO3. That sort of was hidden there. So let's do it different. I don't know what to erase. Well, we won't talk about the Higgs interactions with the, not today yet. No rush, I think. It would be good to keep this somewhere. That A is SW A3. SW sin theta W is obvious my notation, right? Plus CW B, and Z is CW A3 minus SWB. Okay? Just to remember, so once again, when theta W goes to 0, Z is A3. And the question is, why is MW equal there or better? Why is MA1 equal to MA2 equal to MA3? After all, I broke the symmetry. So, let's give it a proof. Let me introduce the following. It looks stupid at the first glance because I'm complicated my life, it seems, but it turned out to be very useful. Instead of working with a doublet phi, Let me work with the 2 times 2 matrix, which looks like this, phi tilde, phi. A 2 times 2 matrix. What is this? Let me just remind you. Phi is phi plus phi 0. And this will be phi 0 star. There is I sigma 2, so it reverses them. So this guy goes up, anti-field, and then there is a minus sign because I sigma 2 has a minus sign. Nothing to it. Sorry? Mahmoud is fast. I sigma 2 phi. If you multiply, you will see immediately. I sigma 2 is just 0, 0, diagonal, 1 minus 1. Notice the determinant H is what? Is phi 0 absolute value square plus phi minus, which is phi dagger phi. So I can work with this invariant. If I like my H, then determinant H is my invariant. You remember what we saw? We saw that phi dagger phi has actually more symmetry. It had SO4. The only thing is I had to look into these components to see how it happens. But look, in the terms of H, it's easier to see. This is invariant node, is determinant H under the following transformation: UL, H, UR. Let's write UR dagger. It's a matrix. You agree? It has SU to L cross SU to R global symmetry. There is more symmetry. Why? Because the determinant of H, of course, these are SU2 rotation, transformation, so determinants are 1. In other words, determinant H goes into determinant UL, determinant UR dagger, determinant H, but this is determinant H. It stays invariant because this is 1 by definition, and this is 1. In other words, the symmetry is SU2L cross SU2R, not U2L, both are SU2, determinant 1. So this is SU2L cross SU2R global symmetry. Of course, part of it is gauged. SU2L is gauged. There is more symmetry, there is extra global symmetry, part of it is gauged. In the other language, we saw it as SO4. SO4 has 6 generators. SU2 cross SU2 has 6 generators. SO4 has rank 2. SO3 has rank 1, SO4 has rank 2. SU2 cross SU2 has rank 2. It's not surprising that it's the same algebra. Same number of generators, same rank. You know, Cartan classifies as all the algebras, okay? You don't get these accidents. Okay, this is one and the same algebra.
How can we see that H, matrix H, should transform that way? U left from left, U left from left.
Not that it should, I'm saying there is this symmetry. I've just proven it. Determinant H is invariant. How did I see that?
Yeah.
Well, I'm smart. I'm sorry. I want to tell you there is no rule. I'm not completely stupid, but it's not me actually. This is not. I can't tell you that. The symmetry is that you will see. How would you see that there was an SO4 symmetry? Well, you have to. I can't give you a rule how to see that there is extra symmetry.
The way we saw it was good, like decomposing into real parts and seeing the whole.
Okay. I wrote it as a matrix, and then I look determinant H. What is the most general symmetry? It will be invariant, and I notice. What can I do? This is a 2 times 2, so I can only do 2 times 2. Unitary transformation, it's a complex. Notice that I took phi tilde phi. Not phi dagger phi as I started on Wednesday, okay? That will be a sub-case, which may be interesting. I have to take phi tilde phi so that it is complex, so that if I have taken phi dagger phi, then it will be Hermitian and it would never transform like this. And I say, what is the most general? I can rotate by unitary transformation on the left. Well, I have to think.
So that is quick step, because I would say that I would choose a random SU2 matrix, and I would say that this has only SU2 symmetry.
And you would be wrong.
Yeah, I couldn't see the hidden.
I know, and you will be wrong, and you know, you will write your paper, and the referee, if she's smart, will say, well, my friend, you're dumb, there is an extra symmetry, and you goofed, you didn't see. But maybe you wouldn't do that, maybe you would pause. Remember what I told you, don't rush. All I can tell you, don't rush. Think some more. That's one of the sort of beautiful challenges when we write our theories, looking for extra symmetry. It's a pleasure of a task, it's like a hard homework. When you give a hard homework, then there is, I gave you a thing to look at the two triplets. And if you don't think carefully, it will be a lot of work. If you think carefully, it won't be a lot of work. Okay, so problems of... In a sense, it's good like that. If, look, think about this, okay, I don't know why you are a physicist. I don't know that. I can tell you why I'm a physicist. But I don't really know. I was like 14 when I fell in love with this game of solving problems. But what I learned, that I didn't have to study that. It was not like biology or geography that you had to study. So the more rules I can tell you, the more you would have to study them. So here the price that you pay is, I have right there less rules, but okay. This is not trivial, saying this. This is a very smart way of doing it. The person that looked at that did a smart thing. The other thing was a bit trivial. The disadvantage of the other thing is that it wasn't easy to see what was going on. Now look at this. What is H0? In this notation, what is the vacuum? Well, remember we said we can choose this to be V. So this is simply V times unity, you agree? Right, in this notation. And I notice immediately this will not preserve all of the symmetry. It will break it. The only thing that remains is when UL is equal to UR. This is unbroken. In the end, we'll erase everything. Because this is too important to be done shyly as I wanted. This is highly not trivial, I want to tell you. This is not something that we would easily notice. Okay, that I'm pretty sure I would have noticed, but I don't.
How do UL and UR look like explicitly?
How do what?
UL or UR as a matrix?
Oh, these are SU2 symmetries. Sorry, when I said SU2, it's they have two different sets of Euler angles. There's SU2 rotations. TAs are Pauli matrices. These are same old SU2. When phi 0, in other words, when phi goes into UL, I don't write this very often, but I should call it UL. Remember, it's good to emphasize because it tells me that only left-handed fermions transform. So it's good to give it this name, UL, to SU2. When phi transforms like this is equivalent to H has the symmetry UL, H, UR dagger. It's there. The equivalent thing was, why? Because phi dagger phi, remember? Phi dagger phi was sigma phi I square, the real components. And this had SO4 symmetry. But SO4 is SU2L. Does any of you know this much group theory? Do you? Have you done this in the group theory class? That's the kind of exercise I would do in my group theory class. In if I were to teach you. First, we show you that SO3 is equal to SU2 as algebra. The second important thing is, because this you run into very often, that SO4 is equal to SU2L plus SU2R. It is very nice to see how algebras that have the same rank and the same number of generators are actually the same algebra. Do you know any other example? Some of you that played maybe more with the group theory, relatively small groups. I write it here. This also appears very often. SU4. What's the rank of SU4? 3. How many generators?
15.
There is one more symmetry which has 15 generators. It's SO6. 6 times 5 over 2. These are anti-symmetric. Remember the generators SOs are anti-symmetric matrices. Hermitian imaginary anti-symmetric matrices. So you have 6 times 5 over 2, which is 15. And the rank actually is 3. And then you, lo and behold, you can show that it's one and the same algebra. Have you seen this before? Or who has not seen it? Raise your hand, please.
I think we've seen that in the level of algebra.
You have seen that.
SO3 plus.
You just have to take linear combination of these SO4 generators that commute to identify them. I'm not going to show that because it's not so important. I said this notation was not very useful because I could see quickly that there was extra symmetry. By the way, would you have done that? You probably wouldn't have done that. You would have written your paper saying that there is SU2 symmetry. And it's not that Weinberg said that there was extra symmetry. People realized that later on. It's not that in the original paper. You don't think immediately of this thing. You have to first to get puzzled. You have to take this puzzle seriously. Why are the masses the same? And then maybe you struggle and you find out. Okay, the advantage of this is that I know immediately that what remains is a rotation when theta L is equal to theta R. That will remain unbroken. That's the SO3. So in this language, this got broken to SO3 through phi 0. Agree? And in the through H0, this goes broken into, we often write like this, left plus right, so to emphasize that it's symmetric, or left equal right, or whatever. But the breaking is the same. 6 generators, 6 generators, 3 generators, 3 generators. By this I mean theta L equal theta R. It's manifest here. Only that will be unbroken. This has to be invariant. The symmetry is unbroken when the vacuum remains invariant. So you see, but these 3 gauge fields, A is A1, A2, A3, or W and Z in that limit, call it. They are triplet under SU2L. Right? By definition, we found out that the gauge bosons are a joint representation of a group always. They go together with the generators. That's a triplet. There are 3 of them. We showed that explicitly. They transform with epsilon symbols. You've done it in your field theory class when you studied Young-Mills. You said that you've checked that they transform with the structure constants. Therefore, they are a triplet under SU2L. But that means that they are also a triplet under SU2L, what I call plus R, because they coincide when theta R is equal to theta L. See, there was more symmetry in the potential, but you decided to gauge only a part of that. Of course, it's not the way it took place historically. You just gauged things, and then you found out that there was more symmetry. But had you written the potential first, and had you decided to study the global case, you would have said, oh, there is the symmetry, okay, but I don't want to gauge all of it. Why? Because I'm building the minimal standard model. What does that mean? I want to build the gauge theory only of those messengers that I've seen in nature. I like left-right symmetry. I was fascinated with left-right symmetry all my life since I was a little kid. Looking in the mirror, I found it crazy that left goes to right. So I would have gauged, I think, both left and right. And it wasn't clear to me, but you know, I started my PhD school, and then I found out that Salam and Patti, his collaborator, said, let's gauge all of it. They had an alternative theory to Weinberg, glacial Salam model. I may have to say something about it, you will see why. It's kind of more beautiful, right? I'm sorry. It's personal prejudice when both is there. It's sort of, there is something upsetting here. Or not. Or you don't care. But anyway, I could have formed another invariant. Instead of determinant H, I could have taken, we've proven it. There is a custodial symmetry. This is unbroken, and the gauge boson must be the triplet, because by definition they are triplet under SU2L, so they are definition under. This is the same SU2L when theta R is equal to theta L. This is why their masses are the same. In spite of symmetry being broken, you see, there are no miracles. You won't find it in physics. You find equality of particle masses or interactions and so on, you would see the symmetry behind. So it's important to have this belief, because there may be a discovery ahead. Instead of a determinant, we are not used to determinant. I could have taken the trace of H dagger H. You would see that that's basically the same thing. I think up to a factor of 2. I think this is twice determinant H. Check it, I'm not sure. Or maybe not, maybe it is. Can someone do it quickly for me? No. Some coefficient here, I don't know. But it's not good that I do everything. It's nice that I leave you some. Then you would say, aha, you would also say there is a more symmetry here. You would say, oh, okay, you would say that I like a question, I didn't want to underplay it. You could have said, well, I see the symmetry, of course, UL, H, UL dagger, you know, that I see. But then you see, because of H dagger H, or because of the determinant, I can actually choose another completely different one. There is more. And this is what I want to emphasize. When you write down your interactions, it's not you who decides how much symmetry there is. And I have no prescription for you. There is 2. Yeah, I kind of thought that there was. Right. Yeah, because the trace, there'll be this thing times unity, and the trace of unity is 2. I think that's what happens. In the case of the determinant, it's just a number. If I could mention this. There, you will see in the, just as we are going through this, you know, I normally when I decide that there is not enough time, okay, some of you guys have questions and I want to emphasize kids more and more, this course will differ, I think, substantially, for example, from the ones in the last couple of years. That either you should say nothing or you should say more. So let me say a little more. Well, sorry. Determinant H is invariant. We could have just written here, as long as H transform. You often find here people using a different combination of fields, and let me then call it sigma, which is H plus I sigma times G. It's often written like this to remind you, this is also 2 times 2 matrix. That these are normally the would have been Goldstone boson, which are phases or the imaginary components in some way of writing, okay, that I can get rid of it. And this is the Higgs. And then notice that trace sigma dagger sigma, okay, then sigma dagger is H minus I sigma times G. H and G are real fields, obviously. I'm taking the analog of my doublet for real fields. So trace sigma dagger sigma, I think, and Nilufar will check that, I think that'll be a factor of 2. Again, because of the unity, I'm pretty sure you will get, yeah, there will be 2 H square plus G square. I'm using a vector notation, this is sigma I, Gi, which is 2 phi dagger phi. The same thing. I could identify this as 4 real components of. So you often find this, okay, there's something called the sigma model in which one uses this notation, okay. In this case, again, you recognize that there is a symmetry here. Sigma transforms as UL sigma UR dagger. This is why I put a factor Y here. I could have taken a Hermitian matrix, but then I couldn't get both of these. A Hermitian stays Hermitian and it will have only U dagger. But this I can do different. So again, you will see it in the same language. And again, the sigma 0, you would of course rotate as we did in the real components. So this would be V times unity. Sorry, there is a matrix here. I should. Of course, it's a 2 times 2 matrix. One forgets to write unity, but it's there. Again, we will see the same thing. I won't want to touch interactions anymore. We studied interactions with Z boson. We'll say more because you did the homework, but not today. So unless you ask me more questions, which I invite you, I will now move to fermion masses, okay? I have nothing more to say about gauge meso masses. Except that their prediction was extraordinarily successful. The numbers that came out from lab agree perfectly with it. Or maybe I could say this, I'm sorry. Or better to say I should say this. Well, I'm not sorry if I should, but I could, so let me do that. Okay, it's sort of the only thing I'm not sure about my notes. Let's see if I can reproduce. Okay, whatever which way we look at it, we found out that potential had more symmetry. Some symmetry remained. And of course the masses are obtained from symmetry breaking. This is why I got the famous prediction. So, no, this should be talked about, not just could. Okay, I'll raise this. And this was just a side comment. I've decided to work with H, so let me give this H. And this is what I should actually talk about. It's famous rho parameter. Because this has been a great success of the high precision of the renormalizability of the capacity to do loops. I claim that the theory is renormalizable. What does it mean? In field theories you get infinities. But the theory is good when the physical quantities are finite. Okay? The infinities have to cancel. So this is a nice example of something that has to be finite. So we define a rho parameter which is a ratio of these masses, which in the limit, of course, constant theta w, I found the reason why they're the same, and this is the reason why they're also the same. The same reason I gave you in the limit theta w equal to 0, I should have said that. Of course, this remains when theta w is non-zero. It's the same potential. I have this extra symmetry. And our famous prediction is 1. But by the way, we did this at the tree level. So what do you think? Will it stay 1? When we include loops? Notice, this is accidental symmetry of the potential only. The other interactions do not respect the symmetry. The path, for example, very important is the interaction of the gauge bosons with the matter. That has only sp2 symmetry. In other words, there will be loop like this. A typical example, you are studying them in QED. This renormalizes the polarization tensor of the photon, but also the mass when there is a mass. So, for example, I could take W, let's say W minus. And what will I have here? Up and down quarks. Agree? Then there will be Z boson loop. What will I have here? I will have either an up quark, this is neutral, or a down quark separately. And now you and I would sit down. This could be, by the way, a nice homework problem. Because the divergences cancel, they have to cancel. And it's wonderful to see how divergences cancel non-trivially, okay? This is what your sort of face should tell you. It's good to see it. You don't have to worry about renormalizing the things, okay? This physical quantity was 1, there was a symmetry behind it. So when I include the loops, infinities must disappear. Otherwise the theory would not be good. So it turns out that rho is 1. So what will the correction be proportional to? It will be proportional to alpha weak. And you will get a famous factor over 4 pi. Typically you get, it turns out that you get over 8 pi. Well, no, the way I will write it, okay, sorry, it's stupid to say like that. Then you will have 1 over mw squared. It's a ratio of the masses. What will enter here will be what will come out from the loop will be the Fermion masses in the loop. The only quantity that has a mass dependent in the loop is the Fermion mass. So I will get a thing which is mu squared plus md squared no minus or plus. We could check that while you think. Do you realize that something like this has to come out? Is that obvious to you? What is wrong in my expression? The second term, thank you. Why is it wrong? Dimensionally, thank you. I should have seen that. Well, I didn't. See, that's what I ask you, okay? Well, I wanted to remember the coefficient. I didn't even check the dimension. There is mu squared, md squared. Now, the thing that you would do, I now invite you, okay? I could do that, but I don't want to do that. So this is a little homework, okay? Exercise suggested. What do you think will happen when mu is equal md? This is very important. I want us to do this very slowly. It would be a great thing to do the calculation, but it's long. We will spend the whole lecture, at least one lecture, probably. We have to remind you of the loops and so on. Okay, well, maybe one lecture, not more than that. So let's just accept the result. Well, think about that. I found a relation which was due to the potential, and that told me that rho is 1. So if rho is to be different from 1, I have to break SU2 symmetry somewhere. This custodial symmetry. And the measure of symmetry breaking is, of course, of difference of the masses in the doublet. Up and down quark live in a doublet. If they have the same mass, you didn't break any symmetry there. So mu2, this is equivalent with having the SU2, how to say, global symmetry unbroken. I need to split up and down. And therefore, when this is equal to this, you get 0. This becomes 0, this quantity here. Sorry, this in the bracket. Please check it in a non-trivial manner. It's just taking the limit here. I mean, this will be m squared, this will turn out to be m squared. One of the masses is m squared, and this thing goes to unity in the limit when mu is equal to md, because this diverges and this diverges, and the diverges cancel. Okay, so you get 0. That's a check.
So we are saying that if theta w is different from 0, mu and md should not be equal. Do we say this statement?
If theta w is different from 0, no. No, I didn't say that. But I don't know if there is a value that is. I don't know why you saw that I said that, okay? Before I say whether it's wrong or right.
No, that's why I messed up. Because I'm thinking like we break the SU2 times SU2 into one big SU2.
Yes.
And we have 3 gauge bosons that could have the same mass, but they do not have. And we can see that they do not have the same mass through the Weinberg angle.
No, well, Weinberg angle is just, no. The question, when I ask the question, why are the masses the same when theta w 0 becomes, why is mz related to mw when they are not? The reason that mz is not equal to theta w is because z is not w a3. No, there is nothing here. It just tells me that there is some missing between SU3 and cross U1, but the same custodial symmetry that in SU2 gives them equal, here relays them like this.
So mz times cos theta.
Right, this is, right, because this is strange. Why would be there a relation like this? Okay, first there are actually 2 relations here. One that W plus and W minus have the same mass, or A1 and A2, that's strange. Okay, and the second thing is, why is that related to the third mass in a well-defined manner? The reason is custodial symmetry. I took the limit so that you can reason better.
So you say that if rho stays 1, then we didn't break the big SU2 symmetry. If it's
no, if cosine theta W1, we just didn't mix the U1 and SU3. That's all. The only thing interesting here, when theta W goes to 0, Z goes to A3. So it's easier to think about that. But the relation remains interesting even when theta W is non-zero. The only thing is Z is not just Z3. This is just normalization of Z, if you wish. Z had an extra normalization, so it was GA3 plus G prime B, so theta W appeared. Because of my wanting to normalize the Z field the same way I normalize the A1 and A2 and A3 field. There is nothing deep here, so it's not so much theta W. The physics is here. When these masses are the same, then this custodial symmetry would not be broken. This SU2 thing that makes the W's be triplets also relates up and down quark. Well, of course, this is negligible. Up quark and down quark masses are MEV. But when does it become important?
Sorry.
Top.
Okay.
Sorry.
So we say
Yes.
this SU2 custodial is unbroken, or no?
I'm saying the knowledge about its breaking in this sector comes from masses being split.
And that means that
Because you see, in order to get a non-zero result, I have to know that the symmetry broken in the fermionic sector. I have to know that the symmetry is broken, okay? And the SU2 symmetry is under this symmetry, they are a doublet. This is SU2L. So the measure of SU2L breaking, for example, is the vacuum expectation value. That's one way to say, and there will be associated thing. Equivalently, the measure of breaking is the difference of the particle masses in a doublet. The isospin breaking, remember isospin symmetry that we used to think about in nuclear physics? Proton and neutron? The measure of that breaking is the difference between proton and neutron mass. When the symmetry is good, particles in a multiplet have to have the same mass. So, although the vacuum expectation value breaks this SU2L symmetry, it doesn't break the global symmetry. But these guys are a doublet under the global symmetry. So in order that they know that the symmetry is broken, their masses should split. In other words, if they have to carry this information, you see, rho is 1. Now they have to tell W and Z that there is no custodial symmetry anymore. They have to inform it through this loop. You see, W and Z don't know that. They want to have the same mass ratio defined like this. But the fermions will tell them, no, wait, it's not like that. We broke that symmetry. But only, of course, if their masses are different. If their masses are the same, then there is no difference between up and down quark. And therefore, the symmetry won't be broken.
So there is no really this custodial symmetry in the loop up to the loop. Correct?
Right, there is no custodial symmetry. Very good. This custodial symmetry is not there.
Because
It's broken by the loops, precisely. It was just this simple potential that I looked at, okay? I could maybe see that by recalculating the potential to higher orders, including fermionic loops in the potential, okay, I could try to do that. But this is the easier thing to do. This is just the loop calculation to the masses. The same diagrams that you do in QED. It's a little easier in reality because you don't have to take the Q square piece out. Just look at the master. This is even easier than the polarization tensor. So we'll see. Since it's so important, we'll decide the following. Either I'll give you some kind of homework or a take-home exam. I will decide, or I will do it in class. Okay, I'd love you to see that. This is what we mean by standard model being a high-precision theory. We do loops like this. The beauty of the theory is that they are finite when we talk of physical quantities, and then we compare with the experiment, and you can measure theta W, you can measure MZ and MW, you can measure the rho parameter. When does it become important? When I take top and bottom quark. If I take top and bottom quark, because why? Because top is very heavy. You see, I'm normalizing this to MW, okay? It has to be, this is a dimensionless quantity, so 1 over MW came out. So when I take M top, which is much bigger than M bottom, notice what happens. This is M top, this is M top, therefore the second term is small. This is proportional to M bottom squared times the logarithm. A logarithm is never big. So in that case, this will be negligible. So I get that rho is roughly, I keep only alpha w over 16 pi mw squared mt squared. I can make you an amusing comment if you wish. Many years ago, 1981, I was interested in the unification of gauge couplings. Supersymmetry became very, very, very popular, and I found it beautiful, or we found it beautiful with my collaborator Bill Marciano and Brooke everywhere I worked. And whatever we did, we needed rho parameter to be bigger than 1 to make some statements. Actually, we believed in supersymmetry. We said we like supersymmetry to go together with unification. It didn't work, but it would have worked if top quark would have been heavy, because notice, there was a prejudice. If you talk to people in 1981, what is the mass of the top quark? Everybody would tell you, oh, it's less than 10 GeV or something. Because look, bottom is 5 GeV, so it will be similar. Everybody had this prejudice, very strange. So we needed rho to be substantially bigger than 1. So we said we need a top quark around 200 GeV. People told us we were crazy, many people. I'm very proud of that. There's a paper, if you're interested, actually, said it. Page number 4 of paper with Marciano, actually we say that the top quark is 200 GeV. We needed it to predict theta W. We said we'll get psi squared at W 0.23. Well, I forget why. It's too early. Anyway, so this rho parameter even historically played an important role. A year later, Podczynski-Wise and Alvarez-Gomez said if top quark has a mass of 200 GeV, we couldn't understand the Higgs mechanism. Okay, I'll try to tell you at the end of the course. I'll try to do the following at the end of the course to tell you why this formal course on supersymmetry, in which you will only learn the algebra, can have interesting impact on the standard model. Okay, I try to, so that those of you who want physics know why you're studying supersymmetry, not just as algebra. Now, forget it if you wish the history. Okay, we know that the top quark mass is almost 200 GeV, right? 175. And this few, whatever it is, what the percent, a little more, a little less, has been actually established experimentally. It agrees beautifully.
When we can speak about loop of triple quark, because it's very heavy, and my idea is that when you have W boson to reduce them, it has to have very large, let's say, energy, and so maybe alpha weak also will change in this case.
Yes, alpha weak is this number.
I mean,
Alpha weak, this is alpha weak, strictly speaking, it will be alpha weak at MW because I'm doing the calculation at the MW mass, which is at number 1 over 30. It's not 1 over 120 or whatever, it's 1 over 30. Everybody's in the loop. Whoever exists will also float in the loop. Remember, in the loop you have virtual particles.
but if you don't have the enough,
They may be heavy, they may be as heavy as you wish, they will contribute in the loop.
even if you didn't have the enough energy to produce them.
Even if you didn't have enough energy to produce them, they are there in the loops. That's a good point that you ask. Yes. And you can see how they can, I'll try to tell you that even if they are extremely heavy, they could have an important impact on through the loops. It's very interesting because their contribution is logarithmically suppressed, but not the contribution. Well, it's too early to give you details. Very good question. And that's their virtuality. But even at the tree level, they contribute. So why shouldn't they at the loop? You can't produce a W boson, so maybe this shouldn't puzzle you. When a neutron decays into a proton, which is the down quark decaying into it emits a W. You can't produce W. This is at the energies of MeVs or something. But it contributes. Of course, you know that it will contribute as 1 over mw squared. So when mw goes to infinity, the contribution will disappear, right? That has to happen. Okay? You know, this is what I keep saying, that the particle is very heavy. The interaction is this in being inertial argument that I use. It means when your mass goes to 0, you decouple. You will always see that. When W mass goes to 0, it doesn't produce weak interactions anymore. And the reason that these guys couldn't see the W was basically infinitely heavy in 1935 and 1945. And in 1950s, people started to think a little bit about the W. You know, as you could start imagining the energies growing. That's a nice probe, for example, whether there is T prime and B prime quarks. They would also contribute here. They would change the prediction unless their masses were the same. Well, they could be accidentally the same and they would cancel, okay. We are now more and more sure that there are no other generations. LHC would have to see these generations. You will see why I say that. Because you could tell me, how do you know that the mass of the extra generation is not 17 TeV? And therefore maybe it's there, but LHC cannot produce it because its energy is 13, 14 TeV, not 17 TeV. You will see that it cannot be, okay? I'll show you that if new generation exists, they must be much lighter than TeV. They must be, otherwise I couldn't speak of the standard model, but that will come. So maybe fermions will leave. It doesn't make sense to start a lecture, a new topic. I could summarize it quickly, but no, it's better that we see if there are more questions.
So we have a model without fermions, just with the positive, but it's not. Okay, so we have this symmetry SU2 cross SU2R, which SU2R is a global symmetry.
Yes.
We break it down, and then it leaves 3 massive bosons and 3
equally massive.
Yeah.
No, there were 3 massive gauge bosons anyway without that extra symmetry. It's just the masses are the same. Right. Okay. Sorry.
We gauge one of the SU2L, but the other one
we didn't gauge. We left as a global, right?
So in the case we gauge both, we will
suppose what would happen if I decided to gauge both. Well, now that you ask, we can do that instead of starting a new lecture, okay? This is not learning today. But before I do that, maybe you have a more pragmatic question?
Very similar to that. Because
okay, so let's talk about that. Well, if I decide both of them, that means, so in other words, I'm saying that there is W plus, W minus, and Z, right? Well, let me call this WL. Why? To emphasize that it couples to. And let me call this EL. It's not completely left-handed, just to emphasize it comes from SU to L. If I gauge the other guys, that means I'm saying that there is also WR plus, WR minus, and ZR. That would be equivalent to saying, add another SU2, you get another set of gauge bosons. Then you would say, well, why don't I see these guys? What would be the answer? Sorry? No, but I want to have a left-right symmetry, okay, if I'm gauging that. No, I can have 2 things. They are weakly coupled, okay, I can take the coupling very small. But another possibility could be that they are heavy. So Patti and Salam said, okay, but they said very sort of shyly, they didn't emphasize it so much, they talk about quark lepton unification. Mohapatra and Patti took it more seriously, but still not enough. Saying, well, maybe, yeah, maybe there is left-right symmetry in nature. You know why? Then it would be sort of nice to understand. There is this question, how this parity breaking occurs in weak interactions? Why is photon completely symmetric and W completely anti-symmetric? If such a theory, the answer would be simple. Just imagine that the symmetry is broken spontaneously. That was the first example I gave you when I started my lectures. I took a discrete symmetry. It was interesting, they didn't take it so seriously. I took it. I saw this, I fell in love because I was always fascinated. I told you, just a childish interest in left-right symmetry. When I saw this paper, I remember my awe when I saw left being right. I said, oh, this must be it. And my first paper actually I wrote with Avi Mohapatra was to show that this can be broken spontaneously. What is the, why do I mention this? Not because of my love for this, but because if the world is symmetric, in other words, it would look like this. No more singlets. This would be the idea. This was the idea of Patisala. This is what they had in mind. The world could actually be symmetric, only this guy is heavy. In other words, the symmetry breaking took place at a larger scale. Notice the difference between the standard model. The standard model, there is no right-handed neutrino, and there is no reason to introduce it because it's a singlet. And I'll show you the standard model predicts neutrino to be massless. So I'm now wetting your mouth for two things that we have to study very seriously. This is very gratifying that the standard model failed. Otherwise, there will be simply no hope, realistic, that there must be new physics. But we know that there must be new physics, because precisely it failed where it was supposed to work. It was supposed to be the theory of weak interactions. Weak interactions are interactions of neutrino. So predicting neutrino mass is a great failure. Notice that in this theory, neutrino cannot be massless. And this was a curse. I was told for quite some time by great physicists that I was wasting my time because neutrino was believed to be massless in the 70s when I started out. But here it cannot be, because look, just like the electron, which gets the mass ELER, this will get the mass nu-L-nu-R. You simply, there is no way out. Neutrino is massive in the theory. Okay. And I may decide to say a few words about this, because this is the theory that gave the reason that if you wish, the reason for the existence of right-handed neutrino, and also the seesaw mechanism. I don't know if you heard of that, which became a kind of the way of seeing the smallness of neutrino mass. It's hidden in the theory, okay. But okay, that was the answer to Nicola. Where's another question?
So if we have this case where we have three gauge bosons, so we break completely the SU2 cross SU2 symmetry?
Yes.
So that means there is no custodial symmetry to protect
Well, it goes like this. This is interesting. This is almost true what you're saying. It goes like this. When you have any theory beyond the standard model now, and this is now a generic, okay, we are chatting, but actually maybe doing a little more important. This is an example of what most of people are doing. Most people believe that standard model is not the whole story. So in other words, there is some true, deep down G true, which is broken to G standard model. At some new scale, let's call it E true, which is broken down to U1 electromagnetic. At a scale, let's call it E weak, which is mass of the W boson. I can call that the scale, the messenger mass. So notice when E true, which is related to the mass of the new particles, okay? So or why don't I call it E nu? True, it's stupid, okay? It's not true anymore. It could be. It surely would be new, but to be true. I sometimes dream that this is true. Okay, I'll tell you my weakness. Okay, I have my doubts, but I also believe it. I've been working for years now, recently again, and you'll see why. E nu would be the mass of the new gauge bosons, there will be a new scale. Notice, if that is very large, just like what I said for the W boson mass, if the W boson mass is very large, if it goes to infinity, there is no W boson. All its interactions will go as 1 over mass squared. So we say it would decouple. So when mu goes to infinity, you can think of mu if you wish, okay? This is what Transvar is teaching you, okay, these days. He's going to teach you that you should introduce the cutoff. And then you can let the cutoff go to infinity, and then you will see that cutoff disappears in a good theory. There will be no physics depending on that cutoff, okay? It is. If it did depend on the cutoff, then the theory wouldn't exist. Imagine that the standard model depends on some new scale, which I call cutoff or mu. If it depended, when that goes to infinity, then the standard model, we could not speak of the standard model. It would always have to say the standard model that came from this theory, there will be infinitely many standard models, okay? And the coupling theorem says, this is called the coupling theorem, when mu goes to infinity, all effects of mu go to 0. That should be intuitively clear. We could offer a formal proof, but it should be clear. If my mass is infinitely big, I will not gonna participate in anything. I won't be able to play football, I won't be able to move anywhere. I basically wouldn't exist, okay, if I'm infinitely heavy. You wouldn't know about me. But it must be like that. Imagine, okay, it's impossible that there is, this is why, you know, decoupling is the basis of science in general. What does it mean when you study science? You say, oh, I'm interested in phenomena, certain phenomena, either certain energy scale or distance scale, and I'm going to apply my tools at that scale, believing that what is happening at the distance is much smaller or energy is much bigger will not affect me. That's why I can speak of a motion of a bullet, says Newton. It doesn't matter that there is quantum mechanics. Okay? Quantum mechanics won't kill that cat. A macroscopic object does not follow under the laws of microscopic, thank God, and that's why the series exists, right? This I cannot overemphasize it, okay? The coupling is the basis of everything we do. Of course, if mu is not infinite, a small effect may remain. So the answer to Nicolas's question is, yes, there is a custodial symmetry in the limit mr. Let me call this mr, the new scale, right-hand scale. When it goes to infinity, I will get the custodial symmetry. That means that rho is going to be 1 plus loops, but also some effects of order mw left square or let's call it ml over mr square. For sure. There will be no custodial symmetry if mr goes down, you're right. But mr has to be large. By the way, in 1981, for example, in this theory, in other theories, you find other reasons why it has to be large. That's the success of the standard model. In 1981 already, a group of people, Bell, Bender, and Sony, found out that mr, which is the mass of this new particle, has to be bigger than 2.5 TeV. The number changed, actually. They had it maybe a little wrong in the beginning, in a beautiful paper. In other words, we knew already in the early 80s that this guy was a phantom particle unless you had a machine like LHC. I had stopped working on this for decades, and I came back only because of the LHC, because LHC is probing these particles, okay? So therefore, the effect is small. There is a custodial symmetry. LHC is telling us that new physics is not closed. So whatever you concluded, by the way, if it didn't happen something like this, then the standard model could not make its predictions. All the predictions of the standard model depend on, everything that I say in this course depends on the correction like this for whatever mu is. So why don't I say here, this would be better, m standard model, which is mw squared, over mu. New physics will enter here. It will enter energy. This is why people are trying to do desperately everything, calculating calculating low energy processes, calculating anything under the sun, to see how this could be there, and then to tell the people at LHC, look.
Are those particles possibilities for to be dark matter?
Sorry, is?
Are there possibilities to be dark matter, to behave and to interact like that?
Is there a dark matter candidate in this theory?
Yes.
In the standard model, there is not. That probably you know, right?
Yes.
You've heard that. Well, we'll study these particles, we will establish. Here, in principle, the right-handed neutrino, if it is very light, this new neutrino, which will maybe be a little strange that it was so light. I can mention it, but it's not the moment, okay? These right-handed neutrinos, not the neutrinos, the couple to the Z boson, you see, this guy couples to the new guys. People often call these guys sterile. Because if you think of this guy in the standard model, the guy is sterile, doesn't couple to W and Z. It's not completely sterile here, okay? Yes, this guy could be, in a certain mass range, could be a dark matter candidate, okay? This was studied by a Heidelberg group and also by us here, by my younger collaborators, Nemeshe and Zan, and myself some years ago. I don't believe that's a good dark matter candidate. I would say in principle, yes, in practice, I can bet that that's not true. The thing about dark matter, I'm not an expert. It would be interesting to see what the experts, but we don't have at the ICTP, nobody's really. There are people who still claim to this day, I can't judge with authority, that black holes, microscopic black holes could be dark matter. In other words, that you don't have to introduce any new particles. Black holes exist. And black holes will come in all sizes. Black holes is a fascinating subject. But I have trouble breaking. I've written a few papers occasionally because there is no information, so it's you can say anything basically. In neutrino physics we have much more information. So neutrino physics is maybe, I'm more attracted to it. But needless to say, it's a profound issue. Okay, I stop here.